I was up all night last night, trying to figure out where the sun had gone. And then it dawned on me. In this video, we're going to define what it means for a function to be continuous, and learn about properties that continuous functions have. Why do we spend so much time learning about properties of functions? Well, functions are a bit like food. It's good to know if food is sour or sweet, salty or bitter, dry or moist, crunchy or soft, and, well, you get the idea. Sometimes we just want a nice, sweet and sour orange. Other times we're hankering for something crunchy, like a peanut. In the same way, it's good to know if functions are polynomials or rational, exponential or logarithmic, periodic or not periodic, increasing or decreasing, and for this packet, continuous or discontinuous. All this talk is making me hungry. Where's my bowl of polynomial chips? So what is a continuous function? Well, informally, a function is continuous if you can draw it without lifting up your pencil, or stylus, I guess. So here are a couple of examples of continuous functions. You can see that I can draw this function without picking up my pencil. Here's another one. I can draw it without picking up my pencil. I didn't have to pick it up right at that corner there. So it's continuous everywhere. And then here are some examples of discontinuous functions. Right here, the function is discontinuous at x equals 2 because there's a gap that opens up. You know, if you were to try to draw this function, you'd be drawing it, then you'd have to lift up your pencil to continue drawing the function up at this higher y value. And then you could draw it from there. The last graph is discontinuous at x equals 3. Because you're going along, you have to draw the function, and you have to pick up your pencil at x equals 3 to draw that dot down below, and then pick it up again to continue drawing the graph. And it doesn't count to be drawing it and then go around the circle and then continue drawing it. Besides, you'd miss out on that dot anyway. So now we're going to shift to a more formal definition of what it means for a function to be continuous, now that we have our tool of limits, our basic concept of limits. So here's the formal definition. F of x is continuous at x equals c, so c is just some x value, if the limit as x approaches c of f of x is equal to f of c. In other words, it's continuous at an x value if the limit as you approach that x value is equal to the function value there. Now, in order for this to happen, f of c has to be defined, and the limit as x approaches c of f of x has to exist, because that's the only way that you can have these two things equal to each other. You can't have like an undefined equaling some other number, or equaling even a does not exist, for that matter. The only way these two things can be equal is if they're both numbers. And so sometimes you'll see books that split this definition of continuity up into 3 parts. They'll say f of c has to be defined, the limit has to exist, and both have to be equal to each other. But we're going to go with just one unified version of that definition of continuity. That's just because the limit existing is implied by the equality, and the function being defined is also implied by this necessity of the equality here. So here's an example. F of x equals sine x is continuous at x equals pi over 2. Since if we take the limit as x approaches pi over 2 of sine x, what do we have? And you can look at the graph for reference. If you said 1, that would be correct. Because here, if we take the limit coming in from both the left and the right of pi over 2, in either case, we get 1. What about f of pi over 2? What would that be? Yeah, it's also 1. Here's f of pi over 2, right here. So essentially, and so you can see that this part of the graph on the left is going to connect to this point right here, and then the right part of the graph also connects to that point, and that's what provides that continuity, that ability to continue drawing the graph even through that point at x equals pi over 2. So a visual way of thinking about continuity is the function is continuous at an x value if the graph on the left side and the graph on the right side both connect to the point on the graph at that x value. Now, if you had something, for example, where here's the point on the graph, but it's not connecting from the left side of the graph to that point, well, that's going to be a discontinuity. Same thing for this last example here. The graph is going into this point here, not this point down here. And so there's a discontinuity. Now you can also define left and right-hand continuity, just like you can define left and right-hand limits. So we would say that a function is continuous from the left at an x value if the limit as you approach from the left of that function is equal to the value of the function at that x value. So if the limit as x approaches c from the left of f of x is equal to f of c. And there's a similar definition from the right. It's just that you're approaching from the right. So as an example, f of x equals the square root of x minus 1 is continuous from the right at x equals 1, because if you look at the right-hand limit, so the limit as x approaches 1 from the right of the square root of x minus 1, what is it going to be? Yeah, if you said 0, that would be correct. Because the graph coming in from the right of x equals 1 is falling down to 0. The y values are getting closer and closer to 0. And what's f of 1? It's also 0. If you were to plug 1 into that function, you'd have the square root of 1 minus 1, which is going to be 0. And that's this point right here on the graph. F of 1 equals 0 corresponds with this point. So coming in from the right, the graph is connecting to that point, and that makes it continuous from the right at x equals 1. Now we can expand this idea of continuity to going from a point, like an x value, to an interval by this definition here. So f of x is said to be continuous on an interval if it is continuous at every point of the interval. So as the example shows, f of x equals 1 over x is continuous on the interval from 0 to infinity. If you look at the interval from 0 to infinity, at every single one of those x values, the graph is continuous. And another way you can think about it is if you can draw the function on that interval without picking up your pencil, then the function is continuous on that interval. But now that we have this limit definition, it's helpful to know that what it really means to be continuous at any given point on this interval. Now, this 1 over x graph is also continuous on the interval from negative infinity to 0, because this left side of the graph is also a continuous function on that interval. In example 1, we're going to just get a feel for continuity. Is a function continuous or discontinuous at any given x value? And here we're going to be given a graph. In a moment we'll look at continuity given a formula, like algebraically, but here we'll do it visually first. So we're going to answer all these questions. For example 1, is f continuous or discontinuous at each x value? And we'll have like x equals 2 we'll look at, x equals 3, and another x value, I'll just peek down, x equals 4. And is f continuous or discontinuous from the left? And is f continuous or discontinuous from the right? So we're going to look at regular continuity, continuity from the left, and then continuity from the right. We're going to break it down into those three situations. And for each one, we're going to decide whether or not it's continuous or discontinuous, and we're going to give the definitional reason for why it is continuous or discontinuous. Now remember, the definition is the limit equals the function value. That's the definition of continuity at a given point. So x equals 2. Is it continuous or discontinuous at x equals 2? Well, what do you think? If you said discontinuous, that would be correct. There's that jump that we have to make to draw this point up the top. This would be called a discontinuity, because we have to pick up our pencil and draw this dot up here and then continue drawing the graph at x equals 2. So we would say discontinuous at x equals 2 because of that. But then from a more definitional point of view, we have to say what is breaking about the definition of continuity? What is making it so that either the limit doesn't exist, or the function value is undefined, or maybe the two are not equal to each other? What is it that's breaking here? Well, if we look at this, the limit as x approaches 2 is what here? It's 2. Yep, coming in from the left and from the right, we approach a y value of 2. In fact, we're staying at that y value of 2. What about f of 2? F of 2 is 3. So the issue is not that that the limit does not exist or that the function is undefined. The issue is that the two are not equal to each other. So a way we could write that out is we could say the limit as x approaches 2 of our function is 2, which is not equal to f of 2. Since f of 2 is equal to 3. So basically you have the limit is equal to 2 and f of 2 is equal to 3, and these two are not equal to each other. So here we're showing that the limit, or we're kind of stating that the limit is not equal to the function value. What about, is the graph continuous from the left at x equals 2 or discontinuous? Well, coming in from the left, we run across the same issue. The limit as x approaches 2 from the left is 2, and f of 2 is 3, and those are not going to be the same. So we can say the limit as x approaches 2 from the left, oops, we're going to circle discontinuous from the left. And that's because the limit as x approaches 2 from the left is 2, and that's not equal to f of 2. Which would be 3. And it's the same thing for continuous or discontinuous from the right. We have the same issue. The limit is 2, the function value is 3. Those are not the same. So we can say discontinuous from the right at x equals 2. So that's x equals 2. Let's move over to x equals 3. We're going to look at those same three things: continuous, continuous from the left, continuous from the right. So let's talk through all of them. What do you think? Is it continuous? Is the graph continuous or discontinuous at x equals 3? Yeah, if you said discontinuous, that would be correct. There's this big jump as you're drawing this piece, and then you have to jump, pick up your pencil to continue drawing it after x equals 3. So definitely discontinuous at x equals 3. What reason could you give for it being discontinuous at x equals 3? If you said the limit does not exist at x equals 3, or as you approach x equals 3, then that would be correct. If you look at the left-hand limit, it's 2. If you look at the right-hand limit, it's 1. And those are not the same thing. And so the regular limit as x approaches 3 does not exist. Let's write that reason out. Discontinuous at x equals 3 because the limit as x approaches 3 does not exist. The left and the right-hand limits don't agree. What about, is it continuous from the left? So if we're approaching from the left of x equals 3, is it continuous? And the answer would be yes, it is continuous. Because look at the graph. The graph is connecting to the dot at x equals 3. And so it's continuous at, from the left at x equals 3. The reason would be just the definition of continuous from the left. So the limit as x approaches 3 from the left of our function is equal to, well, let's get the value here. It's equal to 2, which is what f of 3 is equal to. So there, the two things, the limit and the function value, are both equal to each other, therefore making it continuous, at least from that side. What about continuous or discontinuous from the right? What would you say? If you said discontinuous, that would be correct. So if you look at the limit as x approaches 3 from the right, it's going to be 1, but f of 3 is 2. So this graph here, when we took the limit, it's kind of telling us that the behavior of the graph is to get closer to 1 as x approaches 3 from the right. And that's not going to connect with the point on the graph at x equals 3, which is up here at a y value of 2. So the way we can write that out is, well, first off, discontinuous from the right. And that's because the limit as x approaches 3 from the right is 1, which is not equal to f of 3. And f of 3 in this case is 2. By the way, if you're not comfortable with this chain of equals and not equals, another way you could write it out would be, let me just write it off to the side. You could say something like, the limit as x approaches 3 from the right of f of x is equal to 1, but f of 3 is equal to 2. That would also make it clear that you know that these two things are different, and so we're not satisfying the definition of continuity. So therefore the function is discontinuous at that x value. But you definitely, for these examples, need to make sure to explain why, by the definition of continuity, by the limit definition of continuity, why the graph or the function is discontinuous or continuous. You'll have to show it either way. All right, let's look at x equals 4. Is the graph or function continuous or discontinuous at x equals 4? If you said continuous, that would be correct. The limit coming in from both directions is 2, and f of 4, if you go up to the graph, is 2. There's a point on the graph there with a y value of 2. So we would say continuous at x equals 4 because the limit and the function value agree. They're equal to the same thing. And what about continuous from the left and from the right? What do you think? So if you said that they're both continuous, so continuous from the left and continuous from the right, that would be correct, because the graph on the left is connected to the dot at x equals 4, and the graph on the right is connected to the dot at x equals 4. So continuous from both directions. And if you're going to circle continuous, then you're basically going to be writing out the definition of what it means for a graph to be, or a function to be continuous. So it's going to be similar to the one that we wrote right here, except you're going to have approaching from the left for one, and then approaching from the right for the other. Yep. Clean that up a little. One other thing I wanted to mention is that here, if you find that the function is continuous at given x value, well, then it has to be continuous from the left and from the right. Because if it's continuous, then both the left and the right hand limits are agreeing, and they're going to that function value. So definitely the left and the right sides will be continuous as well. You'll have continuity from the left and the right. And in a similar way, if you've got the function is discontinuous at a given x value, well, there it kind of depends on, so not in a similar way, but there it kind of depends on what sort of discontinuity you have. Like in our first example with x equals 2, we had that the limit actually existed, and there was like a dot up here. But here we had discontinuity from the left and discontinuity from the right. Whereas at x equals 3, the function was discontinuous, But we did actually salvage some continuity from the left right here. The dot happened to be connected to the graph on the left. So when you have this dot that's removed from a continuous function, making it discontinuous, well, there you're just not going to get the continuity because neither side are going to go to that dot. But if you've got this jump in the graph from one to the other, well, then it's possible you could have continuity from one side. Now, if this dot was instead moved up here to be friends with this other one, well, then you may not have the left or the right attaching. So you have to be a little bit more careful when you are circling the discontinuous, the overall discontinuous. You can't just assume that both left and the right sides will be discontinuous as well, like we saw with x equals 3. But if you know that the graph or the function is continuous at a given x value, then you know it also has to then be continuous from the left and from the right. Thanks for watching this part, and I'll see you in the next part.